So yeah, we've been doing a little astro update before the main talk most nights. And so tonight I'm bringing you 2 missions and 2 objects in our solar system being explored. So the first one we'll look at is the New Horizons. Its second chapter where it got to Ultima Thule. And just listening to the little NASA videos, I'm pretty sure that's how it's pronounced. Just to recap on what New Horizons was, or is, it's a mission launched in 2006, January. Got to Pluto in July of 2015 and was a fantastic success. Took a tremendous amount of data and sent back images and just fantastic. This is Pluto, this is its moon Charon. And because of that, its mission was extended through at least 2021. It got funded, that's really nice. And it's off into the Kuiper Belt, objects that are what Pluto is. Pluto is a Kuiper Belt object, king of the Kuiper Belts. And it's going to be at least doing this flyby, and it's going to be looking at other objects from a distance. The object it got to this year was Ultima Thule. That's its official name. I don't think this has been yet fully approved by the International Astronomical Union, but it's going to be hard to change to something else now. It got a lot of press with that name. Ultima Thule was discovered by the Hubble in June 2014. So that is after they took off. They didn't even know it was out there at that time. This was a search for, specifically in this part of the solar system, for objects that New Horizons could get to. They found one, they were able to use Pluto and what maneuverability they have to get there. It's unbelievable to me. I mean, when you think of all the difficulties involved in that, and they pulled it off. The name is a Greco-Latin term for place beyond the known world. There was an occultation around a star that, as far as I can tell, doesn't actually have a name. Telescopes on Earth watched that star vanish, and they seemed to predict a sort of a snowman-looking Olaf shape. The flyby was on January 1st of this year. We know that Ultima Thule rotates about once every 15 hours. Its apparent magnitude is not going to be something you can find in your backyard telescope. It's about 20 miles by 12 in the bigger lobe and 7 in the smaller lobe. It takes it 298 years to go around the sun. It's about 46 to 43 times the Earth-Sun distance away from the sun in its orbit. And its orbit is only tilted about 2.5 degrees, which is much less than Pluto. And there's our first images. I believe this is a composite of 2 colors, false color images, created by 2 successive images as the spacecraft was moving. I think they've tried to create a 3D image from this. Maybe if you have glasses with you, you could try it. Yeah, everyone carries those with you. You never know. You get 3D pictures thrown at you. These 2 objects came together. They called, I think this one is Ultima and this one Thule. I think they decided to give the 2 parts of the name to the 2 lobes here. Definitely in contact here, but they did not have any sort of violent collision at all. There's no debris thrown around, there's no deformation of these 2 parts. So best I can tell, guessing on the composition, density of this thing, they collided at about the speed that you park your car. So they made a little dent in each other and nothing much more. So you probably had some material out here moving around. Those coalesced into 2 objects that were rotating around each other, and then they just kind of very slowly came together and kissed, and now are rotating together as one object around a single rotational axis. And here's a reflectivity image, kind of what you saw in the black and white image earlier. And that's about all I can find. I dug every place trying to see if there are more images or anything new to show, and there isn't yet. And the reason is the download rate when, oh, it should be capital J, sorry. When the spacecraft was passing Jupiter was 38 kilobits per second, which means it would take about 2 to 4 seconds to get one of your emails down from the spacecraft. By the time it was out to Pluto, the signal's getting really thin, and so we're down to 1 kilobit per second. Now out here at Ultima Thule, we're probably down to 800 bits per second. So your typical email would take about 12 minutes to download. So it's going to take a while to get the data from this mission off of the hard drives and down. So it's going to take about 20 months. It'll be through September 2020 that we continue to hear new things come out. Yes?
The transmitter is only 15 watts.
That sounds right. I don't have that in my head. Yeah, 50.
Amazing that they can still get data out of there.
74 times the sun-Earth distance away. And what makes it worse is the Ultima Thule and the spacecraft are behind the sun from about the 4th to the 15th. They're too close to the sun to be worth pointing Earth's radio telescopes at and trying to pull data down. So we didn't even get data right after the flyby, and it's probably just now starting up again. Our second mission is the OSIRIS-REx.
One more.
Oh yes, one more, go ahead.
One more quip.
One more quip. You got.
Holy ski rack. Did that from out of this world too?
Oh, very possibly. It's an old term. So our OSIRIS-REx got to Bennu. This is not way out the edge of the solar system. OSIRIS-REx probe was launched in 2016, got to Bennu in 2018, and it entered orbit on December 31st. So again, it's the day before the flyby out with New Horizons. So excitement happens even over the holidays. It's about 1 mile away from Bennu. It takes 62 hours to orbit, just 1 mile away, because this thing is really small. It's about 1/3 of a mile in diameter, so it would fit easily just between here and downtown Berthoud. So, and what it's going to do is study the surface for quite a good time, looking for the right place to drop a probe that will take a sample. They can do up to 3 tries at it. And the goal is to get this sample returned back to Earth September 2023, and that will be the end of the mission. So here it is coming into a very gentle, slow orbit around something that hardly has any gravitational attraction at all. Bennu is a carbonaceous asteroid. It's part of the Apollo group, and that means it is potentially Earth-threatening. Its orbit crosses Earth's orbit from distance from the sun. In fact, it's potentially hazardous. Has a 1 in about 3,000 chance of impacting the Earth between 2175 and 2199. Again, 30 miles in diameter, goes around the sun in about 1 1/4 years. Bennu is the Egyptian bird of the sun, creation and rebirth, so that's where the name comes from. And that's all I have. So, question?
Not a question.
Oh, okay.
Just an announcement. In April, our speaker will be talking about New Horizons Phase 2 and the Thule encounter. So hopefully we'll get some data. We have John Spencer talking about the New Horizons Phase 2. He works at the Southwest Research Institute in Baltimore, and they've done an awful lot of data. Hopefully they'll have some better pictures that he can tell us more. And it should we get to this place in space. The other thing that I forgot to mention is we are an all-volunteer nonprofit, and we have a nice donation box next to the back door. If you like what we do, and you have a couple dollars or a couple $100 rolling around in your pocket, please don't be shy. Thank you. Tim, there you go.
Thank you. Can everybody hear me? I want to be sure I got this on right. Okay. It's a pleasure to be here tonight. Thank you very much for all coming out on this cold night. We're going to talk about the GOES-R series of spacecraft, which is the next generation of geostationary weather satellites that we launched. We launched one in 2016 and one again this year in March. So we're going to start with a little movie here about weather. Let me start with a little weather primer. You know, a lot of the things that we take for granted, we take for granted the fact that we can see a hurricane coming to the east coast of the United States, or that we can see all kinds of cloud patterns, is relatively new. I mean, the first geostationary weather satellite wasn't launched until 1975. And so for those of you that are my age, I recall as a youngster, you didn't have that. It didn't exist. And you know, it wasn't until later on in my life that we were able to see the kind of things that we see today. And I'll show you where we've gone with some of the imagery that we have. So just as a refresher, there's two types of weather satellites. One's a polar satellite that if you're the Earth, you go around the Earth like this. The other is a geostationary satellite that synchronizes itself with the rotation of the Earth around the equator so that it is always looking at the same spot on the Earth. The polar satellites, that with the United States satellites and the European satellites, all the polar weather satellites that we have give us a revisit time about twice a day over the same spot of the Earth. So if you're sitting on the east coast of the United States and one of the hurricanes, large hurricanes, bearing down on you, to get an updated piece of information about that hurricane every 12 hours is a little unsettling. So the geostationary satellites give you a continual view of what that weather looks like as it's coming towards you, either a hurricane or any other type of severe weather. And as you'll see, some of these satellites, or the capabilities of GOES-R, has a lot more capability than just that. And I'm a little bit, just tell you, I'm a little bit nervous because there should be something down in the lower right-hand corner of here playing. So I hope you got the right codecs for some of the videos I have. So let's go. So this is where they started back in 1966. They launched an experimental satellite called ATS-1 and ATS-3. And if you look at how much these images jiggle around, that's a measure of how not stable the satellite was as it pointed itself at the Earth. It sort of jiggled around a little bit, so the camera jiggled around a little bit, so the images you get look something like that. And so this is that first ATS satellite that they launched. Nowadays,
it
was a spin-stabilized platform, that one was. Nowadays, we have the GOES 16, which is renamed GOES East. So NOAA, the way that they do it, when they build a satellite, it's GOES R when it's on the ground. When we get it on orbit, they give it a number. So GOES 16 or GOES 17. And then once it gets to its final operational position, they call it GOES East or GOES West, because the eastern satellite sits over the equator about a third of the way out across the Atlantic Ocean. And the west satellite, or GOES 17, sits over the equator, about equal with Alaska. So that the overlap of the two of them gives us a full picture of the United States. And we overlap across the middle of the country where you have Tornado Alley and you have a lot of severe weather that you're worried about. So the eastern satellite looks predominantly at the east coast. The western satellite looks predominantly at the west coast. And then there's some overlap across the United States. And then there's a third satellite that is launched into the center of basically the center of the country. And its purpose is that as a hot backup. If one of the two satellites goes down, they can use this satellite to look at either the east coast or the west coast, or they can move it into the other operational position. So we have continuous operational coverage, because the last thing you want to know as a severe storm is bearing down on you that the satellite something happened and you have no data for you. So there's the on-orbit constellation is 3, east, west, and in the center. And then there's a cold spare that's on the ground ready to be launched at a moment's notice should they need it. So what do we do down at Lockheed Martin? We're building the satellites. We're building 4 satellites, RS, T, and U, which became East, West, and then T and U. And we're building 4 of geostationary lightning mappers and 4 SUVI instruments, and I'll explain about what those do. Those look at the sun. So we also build the magnetometers that's on the satellite. So of the 6 instruments that's on the satellite, we're building 3 of them, and as well as the satellite itself. So we'll talk a little bit about the spacecraft. NOAA funds the mission, and Goddard Space Flight Center in Maryland is the contracts us to build the satellite. And then the instruments are built by, there's an advanced baseline imagers built by Harris in Fort Wayne. As I said, we build GLM and SUVI. There's an X-ray instrument that's built by LASP in Boulder. We have a particles instrument built by Assurance Technology Corporation in Massachusetts, and then we build the magnetometer through a little small subcontractor called META. But basically the spacecraft from tip to tail here is about 30 some odd feet, a little over 10 meters long. So the solar array is about 8 meters long. From here to here, it's about 25 feet tall, the spacecraft is. About 20 feet tall, and then the magnetometer sits on a magnetometer boom that extends out about 25 feet or about 8 meters. And there are 2 Earth-facing instruments that do weather. One is the Advanced Baseline Imager, and this is the one that sends back all the images. So I'm sure over the past summer you saw the images of Florence, or the previous you saw the images of Irma or Maria, as you saw it barreling down on the coast. Those came from the Advanced Baseline Imager off of the GOES 16 satellite. And we also make the Geostationary Lightning Mapper, which is a first of its kind, never been flown instrument that looks at lightning from geostationary orbit. And I'll talk to you a little bit more about some of the capabilities and some of the things that can do. There's 2 solar pointing instruments. So even though there's 6 instruments on the spacecraft and it's a weather satellite, only 2 look at the Earth and do weather. The remaining 4 do space weather. So there's 2 instruments that look at the sun. There's the EXIS instrument that looks in the X-ray, and there's the SUVI instrument that looks in the ultraviolet at the sun. And then there's a magnetometer that's on the end of that boom. And then there's what we call an in situ instrument that measures all the electric particles and fields that are coming by the spacecraft at its location. And if anybody has any questions, please feel free to stop. Yeah, go ahead.
Did you say what the acronym stands for? GOES?
Geostationary. You had to ask me that. No, geostationary observational environmental satellite. So, yeah, I've only been the program manager for 5 years. So, but GOES is not just a science satellite. It also has, it's also a communications satellite. Way back when the GOES program was founded, there was no real internet. Okay, so there was no way for the satellites to really disseminate the data, this critical weather data, down to the various National Weather Service offices all over the United States. So what they did is they set up essentially an internet in the sky. And so the GOES spacecraft takes its raw data, sends it down to the satellite facility in Maryland. They process it and send it back up to the satellite, and then it is rebroadcast out to whoever has a transceiver. And so then all the National Weather Service sites, so for the price of a transceiver, you too can pick up all of the GOES data coming off of the GOES satellite, okay? And if you've ever been up in the mountains, and you look in the mountains and you see one of those small little weather stations that has one of those solar panels on it and a little antenna sticking off of it, well, there's about 20,000 of those across the northern hemisphere that monitor pressure, temperature. Some of them monitor river flow. Some of them monitor tidal motion. The GOES satellite asynchronously communicates with all 20,000 of those little weather stations, takes the data and sends it down to Maryland, where it's incorporated into the weather models. So it's a fairly sophisticated comm satellite in addition to a science spacecraft. So this is just a little stop-action movie, if you will, of us building the satellite. So our satellite comes in two pieces, or we build it in two pieces. One's the propulsion module that contains all the propulsion equipment. The other is what we call the system module. And then we put the two of those together. And this operation that you see that takes here about 3.5 seconds is actually a 4-hour lift operation. And the clearance between those two pieces of hardware is about that much. And so that's the large advanced baseline imager getting installed. This is the solar array being deployed. And so those are normal sized people. So we're on our way to thermal vacuum. So that gives you a feel for the height of the spacecraft. We're going into the thermal vacuum chamber back at Lockheed Martin. We deploy each one of our appendages to make sure that they work. This is the X-band antenna that's going out. This is the antenna wing that's being deployed.
Really dumb question. What's
Yeah.
the suits?
What's the suits?
Yeah.
Oh, sorry, those are the clean room suits. I got to stop before I answer your question. I got to tell you, my grandson's favorite part of all of this is that you drive a truck into the airplane. Okay? That's his favorite part of everything. Okay? But the suits, everything we do on the satellite's done in a clean room, okay? And there's various classes of cleanliness for the clean room. We vacillate between a class 6 and a class 8 clean room, which means the number of particles that are in the air. And the reason we do that is for a number of reasons. One of the instruments on there, the X-ray instrument, if you take the oil from one fingerprint, and you get it within about a meter of that instrument, and it stays there, that's enough to corrupt their science. So, so everybody's in suits. They're gloved up. The gloves are taped. Full beard covers. So we do that to make sure that we don't corrupt the science. So there's both particulate contamination, dirt, dust, that kind of stuff, and then there's molecular contamination. So we're protecting from both of those. And when we build satellites like OSIRIS-REx, that he just talked about, we also do amino acid cleanliness too. We have to make sure that we don't contaminate the sample that we're going to go out and get with our own amino acids and say, hey, look, we found life out on Bennu. Okay. So the other thing I want to talk about here is if you look down here, this is the amount of data in terabytes, okay, that each of the each of the constellation of satellites, geostationary satellites, has returned since 1975, okay? And if you add all that up, it's this lavender line right here. So within about 2.5 years, maybe 2 years, probably another 6 months from now, we will have returned with the 2 GOES satellites more data than has been returned to the Earth from all the other geostationary satellites combined. So we return about 1 terabyte a day, a little less than 1 terabyte a day. So last year on the one satellite, we sent back 300 terabytes of data and 18 million images of the Earth. So it's a lot of data. And so you think about the magic that's in the satellite, there's a lot of magic in the ground system too. Because the ground system has to be able to process this data in a fashion such that it can get into a forecast, okay? And when we talk about some of the instruments, I'll talk about how fast that has to happen. It'll really surprise you.
What is the power system on the satellite, and how long is it expected to last?
So the solar array is the power generation side. Okay, it's DC. And we run a 70 volt bus. So there's 70 volts and 28 volts, depending on the what we're doing. Most of the bus runs on a 70 volt bus. And the life expectancy for the satellite is 5 years of storage and 10 years on orbit, so 15 years. So these are just some, call them baby pictures, if you will. This was when we were on the shaker. We have a big shaker system where we test the satellite for vibration to make sure that it'll survive the launch. And so this is on the shaker. And then this is what we call our acoustic chamber, where it simulates the rocket noise. So, we get to levels in that chamber that would kill you. It's 140, 150 dB in that chamber where we test the satellite to. And so these are folks that were putting it into the acoustic chamber there. This is the thermal vacuum chamber. So there we have a 29-foot diameter by 65-foot tall thermal vacuum chamber where we lower the satellite into. And then what we'll do is around this satellite, we'll build a little cage where we can specifically control the temperature of various pieces of that satellite to take them to their operational temperature while in the chamber. And we can take the satellite through a series of tests to make sure that it operates the way that it should at both cold temperature, hot temperature, in a vacuum. So this is what the satellite looks like fully deployed. So here's the large array we were talking about. And then this is the antenna wing. It's not deployed. This is the advanced baseline imager. Okay. This little platform, just for perspective, when I stand there, comes up to about here on me. So that gives you a feel for some of the height of what we're talking about. Let's talk a little. Sorry?
Is in Littleton, these pictures?
These were down in Littleton, yeah. Mm-hmm.
And Tim, is that
Yeah.
taking any nighttime photos or just daytime photos? Can you take pictures in infrared or any in the dark outside or just during the day?
You are perfect straight man. You had a question?
TVAC chamber, how cold and how hot can you be?
We can get down to about minus, we don't run liquid helium, we run liquid nitrogen to it, so we can get to minus 145-ish down in there, and we can get up to plus 150 C, so pretty cold and pretty hot. So, this is the advanced baseline imager, and this is about my height, give or take, and maybe from me to you in size. And you asked me about whether it's just visible. There's 16 channels on that imager. There's 2 visible channels, and then there's 14 infrared channels from shortwave to longwave infrared to look at various things. So we have channels that are tuned specifically to look at clouds and look at moisture in the clouds. There's a channel that's tuned to look specifically at fire, one that looks at vegetation. There's ones that look at snow and ice, and there's also ones that look at aerosols, and that's code for dust, okay? And so so I'll show you some of the different types of imagery that this presents in a minute. And the capabilities, we've gone from the old imagers had 3 times less spectral information. So we've tripled the amount of spectral information. We've the spatial resolution is 4 times as great, and we go 5 times as fast. So it's a quantum leap in the capability of the instrument. So if you look up here, this gives you a sense. This is an actual GOES picture, so it shows you every 15 minutes or so we get a full disk image, and so you're you're scanning the Earth. You can see the Terminator go across right there. Right next to it, you see the frequency that you get the same images from the old imagers, and so you go click, click, right? And so it would be every 3 hours you get a picture of the Earth, okay? And if you look locally, okay, you see this one will move, then this one's spinning constantly, right? There's a phenomenal difference between the speed of which we get pictures, okay? There's 2 what they call mesoscale image capabilities, and you can move those around all over the country. And if you put them right on top of each other, you can take an image of a storm every 30 seconds. Okay, you can take a 1,000 by 1,000 kilometer image every 30 seconds. And so some of that imagery that you saw over the summer of Hurricane Florence spinning as it was coming into the coast was taken in that mode where we put the 2 mesoscale imager capabilities right over the top of each other and got 30-second imagery.
Is the ozone layer studied with these satellites, or is that a different?
No, that's a little different. This one doesn't do that. We also have the other weather instrument is a geostationary lightning mapper. And the reason that this is important is, there's lots of lightning measurements. You see them on the news. If you watch the news, you can see the, call it whatever it is, Doppler 4000 or whatever they have today. They talk about lightning, and here's the lightning strikes, right? Well, all that measures is cloud-to-ground lightning. It's not measuring the cloud-to-cloud lightning, okay? And the larger percentage of the lightning is actually cloud-to-cloud rather than cloud-to-ground. So the geostationary lightning mapper, or GLM, measures all of the lightning, both cloud-to-cloud and cloud-to-ground lightning. And you say, well, gee, that's cool, but why is that important? The reason it's important is because if you look at this red line right here, okay? What happens is, as a storm is building in intensity, okay, it's building, the number of lightning strikes is increasing. And then what happens is, as a storm is about to spawn a tornado or a supercell, the amount of lightning heals over because it's taking that energy, if you will, that's using the formation of the lightning to form a supercell, okay? So what they've done is they've turned this into an algorithm where they're counting lightning. They're monitoring this, okay? GLM takes a picture of the Earth 500 times a second to detect lightning, okay? And we've turned that into an algorithm and have made it so that we can predict tornadoes. Currently, the average tornado warning time in the United States, roughly 13 minutes, is an average warning time, okay? We're hoping to double that, get it to 20 minutes, 25 minutes. Imagine the difference that would make for you if you were in a tornado that you had 25 minutes to get away from it as opposed to 10.
Jim,
Yes?
what is the aperture of these instruments?
So the aperture of the GLM is about like this. Okay, the aperture of the ABI is about like this, and for ABI it's just fixed by physics, right? I want to look at the whole Earth. I want to have a certain pixel size on the face of the Earth, which is about 0.5 kilometer, and it's just fixed by physics. Same with GLM. GLM's pixel size is about 8 to 14 kilometers, depending upon whether you're in the center or looking out at the limb. Okay.
One more question?
Yeah.
And that's imaging in infrared, or what's?
Yeah, it's imaged at 777. So yeah, it's in the infrared. And so we're looking at lightning strikes in the infrared, so we can look through the clouds, so we can see the lightning in the clouds. Okay, so those are the 2 weather instruments. There's 4 space weather instruments that I want to talk to you about. But first, I want to just refresh everybody's memory about what space weather is. Right? The sun is constantly spewing stuff out. Okay, and some of that stuff harmlessly winds up in space. Others of it heads towards our planet. And the magnetic field of the Earth protects us from most of it, okay? But sometimes it can get through, it follows down the field lines, and that's what forms the aurora that we see on the Earth, okay? Other times, that energy that comes down through those geomagnetic storms can do all kinds of damage to things on the Earth. It can damage satellites. It can disrupt communication in cables. It can form form corrosion by setting up currents inside of the Earth. They can do all kinds of damage. Okay, so space weather is relatively important for our daily lives. I mean, a lot of the high-speed data transmission that takes place between banks, relies on millisecond timing, right? If you have interruptions of that, it screws up all of the high-speed trading, all kinds of stuff, okay? So what we do is the sun, the different phenomena from the sun have different time scales that they get to the Earth. Okay, so visible light takes about 8 minutes to get to the Earth. A flare, an X-ray emission from a flare takes place after we see that flare, then the X-ray emissions come. There's radio noise that comes, there's energetic particles. They all take different periods of time. So we get to exploit that in the way that we look at the sun with our instruments. So the SUVI instrument, okay, looks at in the ultraviolet, but it's an imager in the ultraviolet. And so what that does is it tells us when a solar flare occurs, okay? The EXIS instrument looks at the sun in the X-ray, and so we can use that, the X-ray levels that's coming from the sun to determine the strength of what that solar flare looks like. NOAA has another spacecraft called Discover that sits about 1 million miles from the Earth at one of the Lagrange points, which is the place where the gravity of the sun and the Earth are balanced. And so Discover gives us about a 45-minute warning time that that storm is coming to the Earth, because even though we can see it, it's really hard to determine when it's at the sun whether that flare is coming right at us, because when the Earth is moving, the sun's rotating. It's really hard to tell whether it's coming right at us. So the Discover spacecraft is like a tsunami buoy or a tsunami beacon in space, okay? So it warns us that this storm is coming. Once it gets here, okay, we have a particle instrument on the spacecraft that determines how strong that storm is when it gets to the Earth. And then the magnetometer tells us what it does to the magnetic field of the Earth. Okay, so all these things work in concert to help us to understand space weather. All this data is sent down to the Space Weather Prediction Center in Boulder, and they issue a space weather report every day, just like the National Weather Service sends out a weather report. The SWPC sends out a space weather report every day.
Is there an app for that?
There actually is, I think. I mean, no, you can go online and get it.
Underground?
You can go online and go to the SWPC site and you can get all the data off of their weather report every day.
What did you call it? Swipsy?
SWPC, Space Weather Prediction Center.
Okay.
So if you just type in Space Weather Prediction Center and you can pull up the data. Yeah, and it'll tell you more than you probably want to know about space weather.
I wasn't worried before, but I am now.
Yeah, there you go. Yeah.
Well, we have a YouTube channel, and we've had a speaker, more than one, talk about space weather, and really excellent talks here. So if people look for the LTOs YouTube, they can go back and play them.
Okay, there you go.
Thank you.
So, yeah.
Do you use that data to have the satellite respond then?
So we don't use the data on board with a satellite. We do use it for diagnostics. If we see something odd on the satellite, first thing we'll do is we'll look at the space weather and see if there were anything odd. Okay, we had. I'll just tell you this. One of the instruments reset on us once. One of the solar instruments reset. And we looked at what one of the other space weather instruments was saying, and there was a huge influx of what they call relativistic electrons, okay, that upset the instrument, okay, built up a charge and upset the instrument. And so we do use it in that way. So I just we'll go through launch. This is what we launched on an Atlas 541, so that means there's 4 solids, 1 Centaur. It's an Atlas 5. And there's a little lowly gold satellite sitting on the top. I'll show you. This is what it looks like. If you're inside the fairing after we button it up, this is what it looks like. So this is the satellite looking up. These are the 2 sides of the fairing. And you go, hey, it's blue. Those are what they call acoustic blankets that are glued to the inside of the fairing to keep the rocket noise down from totally damaging the satellite. So that what gets us the acoustic levels that we wanted. Otherwise, it would be way too loud for us to launch. So these are just some inside pictures. And then you can't do any one of these without a real launch video. So these are some launch pictures across the top, and you can see us. What I did is I cut all the good parts together, and so that's coming off of the pad. This was in March of this year, and so you can see the 4 solids. That's down the beach at Cocoa as we're going up, and that's as it's going through maximum dynamic pressure. In a second here, you'll see the solid rocket engines peel off. So off of one side, and then you'll see the fairing separate. So there's the fairing separate to expose the satellite, and there the fairing goes. And then there's the ring that falls down. And next you'll see this is the separation of the first and second stage. So you'll see the first stage fall away. You'll see the engine light. And then last, you'll see the spacecraft separate. So of all of it, this is the most important to me because I want to know that my satellite looks okay when it leaves. Used to be, when I first started this, there was none of this. There was no cameras, no nothing, right? You didn't get to know what your satellite looked like. You just sent it off, and now at least you can look at it and see that it's okay. So
Do you watch your deployments? And how many
we don't get to watch our deployments because we don't have onboard imagery on the satellite to watch the deployments. On some of the spacecraft, we've been able to actually use the science instruments to take a picture, sort of a selfie of the spacecraft, and you can tell that the solar array's out in the right spot, or the antenna's in the right spot. Basically, the best indicator of whether the solar array's out is the amount of power you're getting. So if you're not getting the right amount of power, you know that something's wrong. So now we're going to talk about some of the imagery that's coming down on orbit. So as I mentioned, there's 2 kinds of satellites. There's LEO satellites, low Earth orbit satellites, and there's geostationary satellites, or the polars and the geostationaries. Okay, the polar orbiting satellites are about 400 miles up. The geostationary satellites are about 24,000 miles up. Okay, so this is quiz time. We happen to have one of the LEO satellites going over the same spot of the Earth where we were looking at on GOES 16. One of these is LEO, one of these is GEO. Any guesses? Yeah.
So the left one's Leo or the right one is Geo?
I don't know, you tell me. What do you think?
Yes.
You actually, yes?
I think the right one's Leo and the left one's Geo.
Actually, this one's LEO and this one's GEO. So I think you got it right. Okay, good guess though. But the point is, you can't really tell by looking at the imagery. And so the spacecraft, the GOES spacecraft, is such a quantum leap, if you will, in our capability for monitoring the weather that you can't tell the difference between LEO and GEO anymore. Yes?
Is Leo higher and Geo lower, or which one?
GEO is higher. It's 24,000 miles, and LEO is 400 miles. So a lot higher. So this is GOES imagery of Hawaii. This is why everybody wants to go there. So you can see the upper level clouds moving in one direction. You can see the lower level clouds moving in the other direction. And you can see the convective clouds right here off the surface where the winds hit the island. You can see the convective clouds forming here and down here. And so this is one of the first. This is actually one of the first images returned off of GOES 17 not too long ago. And so the reason it says this is the GOES 17 is not GOES West. It's not operational, so I have to put this little disclaimer on it. NOAA makes you put that little disclaimer on it. Not that you guys are going to do anything with the pictures anyway, but so this is the class of imagery that we get off of the GOES satellite for monitoring clouds and severe weather. And this is in the visible. Okay, these are visible images. Yes.
My Uncle Kirk is probably in that picture.
You think? Is he right here? You think? Yes.
So it sure looks like you're looking straight down, but yet the satellite is geostationary.
Yeah.
And so is it doing correction for as it's further away from
Yes.
what it's directly overhead?
Yeah, so the imagery is all corrected for, it's corrected for the fact that the distance is different, right? From as you're looking off here. And it's also corrected for angle. So, but it certainly gives you some stunning imagery. And so each of these pixels is about half a kilometer big. So the Earth, you talk about your cameras, you're excited because you got a 24 megapixel camera, this is 30,000 pixels by 30,000 pixels, okay? So that gives you a sense of the size of the camera that we got on there. Yeah?
So if you zoomed in on that, can you zoom in quite a bit more and still get resolution, or does it pixelate pretty quickly? Or
it doesn't do, it's not like you're gonna see houses and stuff. Right? That's not the resolution that you got on here. It's not like say a world view, like the digital glows guys fly. It's not like world view, but it's not like a spy satellite, which I wouldn't know anything about. But you can zoom in on that quite a bit, in fact. So here's some other imagery. So this is an infrared, this is in the infrared, okay? This is at night through full cloud cover, okay? And so what you see here is you see these lines you see across, this is the Pacific Ocean. These are ships in the Pacific Ocean at night, okay? And so what happens is the smokestacks emit whatever their byproducts are from their soot or whatever, and it changes the infrared properties of the clouds enough that you can see their trails as they cross the ocean. Pretty cool, huh? And if you remember the eclipse from not last year now, but the year before, okay, this is what the eclipse looks like from geostationary orbit. So you can see the shadow of the moon as it goes across the Earth, right? And so you can tell that the full eclipse, right, was right through here, right, because that's where it's dark. And then over to the right or to the left, you see it's not quite as shadowy, right, as you're going through it. So it's just a completely different view of an eclipse. Everybody ran out and saw the eclipse in 2017 because you could, right? And we had pretty good. I happened to be in North Carolina on vacation that week, but you had about 80 or 90% coverage right here, and so it was pretty cool. So, but that's what an eclipse looks like from geostationary orbit. So the other thing, as I mentioned, that the satellite has the capability not only to look in the visible, right, but it can also see aerosols. And so this is, you can see this little thing right here. This is a volcano down in Mexico. And this is Sabancaya volcano in Peru. So you can see the ash cloud that came out of that volcano when it erupted. Okay? And that's all interesting. It makes for good, cool pictures, but it's not necessarily scientifically valuable. If you look at this one over here, okay, this is the Galapagos. Okay, and what you see here is this is an infrared image, and this is there's a sulfur dioxide capability on board that we can measure sulfur dioxide. And so what you see is this is the sulfur dioxide cloud that came out of that volcano once it erupted, right? And so they can then track the sulfur dioxide as it moves across the Pacific Ocean to the coast of South America. Okay, and this is the more valuable information that the satellite produces. We're so accustomed to looking at the world in the visible, right, that we don't realize that there's an entire range of information out there in infrared or ultraviolet or X-ray that we can exploit for understanding our natural environment. So, yeah.
Is that little red box like a extreme heat signature from the volcano or lightning or?
As the video plays on the Galapagos, there's
Yeah, I'm looking. Yes, yes, that's what that is. There's a That's one of the thermal channels. So that's just pointing out here. That red box is pointing out the hotspot, the thermal hotspot in the image. Okay. Yeah, I should have mentioned that. Thank you. The other thing we can do is we can overlay. We've got each of the pixels on that imager is co-registered, right? So there's 16 different pictures that you take in each of the different frequency bands. So if this is a visible image, so you can see the clouds, okay? So you can see the clouds boiling, and this is Hurricane Michael as it came on shore at Florida. And what's superimposed on top of it is they take one of the infrared channels, which in this one it happens to be cloud top moisture, which tells you about the energy in the storm. So they superimposed cloud top moisture on top of the visible image so that you can see what the storm's doing, and then you can also see the amount of energy that it has, right? And so obviously red is a lot of energy, right? So you can see it here. You can also see it out here on the front edge, on the leading edge of the hurricane as it comes in. You know, you always heard northeast quadrant of the hurricane's the worst, right? Well, there you can see it, right?
Question.
Yes?
Do you have multiple array sensors running in parallel so you can do these in parallel, or do you have to sequence images to overlay with filters?
There's multiple sensors running.
Okay, so your image splitting. Okay.
Yeah. This is an interesting one. You can see this is an island right here, and you can see the clouds motion here, and you can see the vortices that are formed by that island as it disturbs the clouds as they go by. It's the wake essentially of the island in the clouds. So these are what they call Vonkarman vortices. That's their name, and you can see them, you know, in real life as you go by the. We've never had the capability because we haven't ever been able to take images this fast to be able to see them in motion, right? You take a picture and then you wouldn't be able to see them moving. This is again over in the Pacific. So this is one's really fascinating to me, but you see the waves in the clouds? So something will disturb the clouds, and you can see the waves as they ripple out from the various locations right here. The other interesting thing is that everybody remembers the fires in Northern California. Okay, so this is another blended product. Okay, those are not the actual fires from orbit. Okay, what they did is they took the color imagery and they superimposed over the top of it what they call the fire channel. And they color coded it to look like a fire. Okay, so there's no heat over here, there's heat right there. So that gives you the location of where the heat is. The visible gives you the location where the smoke is coming off of. Okay, and you say, well, gee, this is really cool for being able to monitor the fire, okay, which is important for as you're watching the fire progress. What's really more important is you want to be able to predict. Okay, and to be able to affect the fires before they turn into something like this. Okay, and here's an example. This was in Louisville, Kentucky. So the guy at the National Weather Service, the field office, okay, was looking at his data, and he sees this hot spot in his thermal data. And he says, gee, I wonder what that is. He calls up the local fire department and says, hey, at these coordinates, there's something funny. Will you go check it out? And there was a barn on fire, okay, that nobody knew about. Nobody had reported. Nobody had called in, right? The fire department could go there and could put it out before it became some kind of wildland fire that created damage far in excess of a single barn burning. Okay, and so if you think about the capability that we have, we've got the capability to detect fires. There's satellites on orbit that monitor vegetation health. There's other satellites that tell us we know what the altimetry of the ground looks like. Okay, we know what soil moisture looks like. There's satellites up there that do soil moisture. There's satellites that do other moisture up there. If we can synthesize all that information together, and we see a hot spot or a series of hot spots that take place, we can perhaps one day be able to decide which one of these we need to go put out first, because the winds are blowing this way and the soil is dry as a bone in this area. We need to go put out this one before we put out this one, so that we can stop these kinds of things from happening in the future. So this is very interesting. I know that especially, all of you that clean your houses are just aghast at the amount you leave, and you go somewhere and you come back and there's dust, right? And you go, where did the dust come from? I cleaned my house. Where did it come from? This is the coast of Africa, okay? This stuff you see right here is Sahara Desert dust that blows across the Atlantic Ocean, okay? And it gets entrained in the winds, and it comes to the United States and drops out. Comes to South America and drops out. So it is not your fault, okay? So you are cleaning your house as well. It is not your fault. And so the reason I show you this is because, this was the summer of 2017, okay? And so this is that imagery that we get every 5 minutes. We get a picture of the Earth every 5 minutes. And you can see the hurricanes march across. So this is Irma. This is Jose. Right, so they march across the Earth. And the interesting thing is you can take this, you can take the desert dust, you can take the smoke, and you can start to fuse all that with modeling. Okay, and what this is the summer of 2017. You can see the fires here. Okay, you can see the dust coming across from Africa. Okay, what's at the center of every drop of water? Dust. Okay, do you ever wonder why all the hurricanes form down here? Okay, it's because you have a constant source of dust. You've got a constant source of energy from the warm tropical waters. Right? It's a breeding ground for hurricanes. And so this is the fusion of modeling and observations, and they can combine the two. And these are some of the kids. Now, does anybody remember Ophelia? No. Yeah, no. That's just a testament to life that nobody remembers if you come in second. Okay? Because Ophelia was this lame little of tropical storm that really didn't do anything. All right. So this is where we're going. This is where we're going. This was done by the folks up at the Numerical Prediction Center, Goddard Space Flight Center. Because we have two satellites up there now, we have GOES 16 and or GOES East and GOES 17. They can fuse the data from the two satellites, and so this is a moisture plot of the entire western hemisphere. From the two satellites, because you can see this one, it kind of dips in here and dips in here. There's a fusion of the two of them. And so now we're able to take the satellite data between the two and do much more, because we have two satellites up there than if we had just one satellite. So let me switch to lightning for a second. So this is a storm over Louisiana and Texas. And so in the back, you see the colors. What you see there are infrared imagery of the moisture and cloud energy of the storm. And what you see superimposed on it is lightning strike data from GLM. Okay, this was from April of this year.
Now, is that cloud to cloud one?
That's all lightning, cloud to cloud and cloud to ground. Okay, and the interesting thing is, this is a storm from the 27th of December of this year, okay? I want you to look at the magnitude of this. This is Louisiana, this is Texas, okay? This is hundreds of kilometers long, okay? What we did is I showed it to you sped up, and now I'm showing it to you real time. So this is what that looks like real time. And I want to go 1,000, 2, 1,000, 3, 1,000. The propagation rates on some of this lightning are over 100 kilometers a second. Okay? And look at the extent of this lightning. You know, it's up into Oklahoma. It's tremendous, the capabilities that we have now to see this kind of stuff and to be able to slow it down or speed it up and understand how it all plays together. And the other thing that we're doing is, you look at this picture, you see the little red dots? Those are airplanes. So we took the FAA database of all the plane transponders, okay, and we plotted that over this lightning storm. Now you watch, you can see the planes zipping around and trying to go around the lightning, okay. But where we're getting to is we're getting to where we have the capability now to monitor this lightning at a scale to where we can hopefully affect air traffic control by helping them to understand where the lightning is, so that when you're flying from New York to Colorado, you don't go via Texas because they just want to fly around the whole darn storm, right? It takes you 5.5 hours instead of 4 hours. Yes?
The planes were not crashing into each other, were they?
Nope, they weren't. But you know what was stunning to me was how many airplane flights there are at night, right? It was really amazing. So let me show you something else. This is what, as I said, this is what the normal GLM data looks like, right? This is a lightning storm that was almost across the continental United States, or 2/3 of the way across the United States. But occasionally, we see something like this, okay? There's no clouds around it. We just see a lightning blip, okay? And you go, well, gee, that's relatively uninteresting to me compared to the lightning that you just showed me, okay? Except if you had been on the ground, it looks like this, because it's detecting bolides or meteors as they come into the Earth's atmosphere, okay? Because it's a hot object that emits at the similar frequency to what we're monitoring lightning at, okay? And so what we found out is that GLM is an absolutely fantastic lightning monitor. Because we take a picture of the Earth every 500 times a second, we can get very detailed light curves that tell us the size of that meteor, okay? And in fact, NASA Ames has set up a system that they take the GLM data raw and they extract all of the all the meteors that they see as it comes through, okay? And now the fact that we have 2 of them on orbit allows us the capability, as we're looking, we can determine what their trajectory is and what their velocity is as they come through and they break up, okay? So it's really, the folks that study meteors are incredibly excited about the capability that we have with these 2 satellites. And this is just we never envisioned or even imagined that we would be looking at meteors, that the instrument would be capable of seeing this, or that you could extract this kind of data from the instrument.
And you can do that during the day?
Yeah, you can do that anytime. I mean, I can do it in full sunlight at noon, because we can see lightning. We have over a 95% detect rate of lightning in full sun. So let me switch to the sun for a second. So the SUVI looks at the sun in 6 different wavelengths. That each of the wavelengths does something different. It monitors a solar flare. Those are the flares that come off of the sun. It looks at active regions on the sun. So you see these black things are called coronal holes. These lighter spots are called active regions. And solar filaments are these little wispy things that come off of the sun. Okay? And so we monitor the sun in 6 different frequency bands or wavelengths, so that we can make different kinds of measurements. Okay? And this is a full rotation of the solar disk from the SUVI instrument. So you can see some of the hot spots on the sun. You can see some of the coronal holes. And there was a partial eclipse that took place in August of this year. And so that's SUVI monitoring the sun, and you can see the moon go in front of the sun. And then last year, there's some examples of solar flares, okay? Last year, there was one of the largest solar flares that had occurred in a decade. It was a class 9 solar flare. And if you, I hope this replays again. Look at how much of the sun rings when they fly. Almost half of the sun, it disturbs the atmosphere, call it the atmosphere or the corona of the sun, almost a third to a half of it. It's a gigantic solar flare. Thank goodness it was not pointed at the Earth. Okay. So let me finish up with this, and then I'll take any questions that people have. Right after we launched GOES 16, we got this, what looks like a really crappy picture of the Earth, right? And we noticed this little thing over here, right? And somebody said, well, what is that? And so they blew it up, and it was the moon, okay? And you say, well, gee, you know, the instrument's designed to look at the Earth 24,000 miles away, right? The moon is 250,000 or 2,400, 240,000, whatever number you want to pick away. And you say, gee, that's a nice picture of the moon. Let's blow it up even further. And it's like, wow, that looks pretty good. And it keeps going, okay? And so the camera and the capability that we have on the satellite, this is a culmination of a number of people who are incredibly devoted to what they do. And to be able to take, and from 10 times the distance that you're supposed to be looking at something, have a pointing platform that is so stable that it's able to bring back images like this is really impressive. When I talk to, you know, my team, I remind them, and they all feel it every day. There are very few things in life you get to do that touch hundreds of millions of people. You know, the satellites that we build for the weather satellites literally touch hundreds of millions of people's lives. And, you know, it's an honor to be able to do that. So, yes, you had a question.
So whoever was asking about the space weather app, it's literally called the Space Weather app. $2.99 on the App Store.
There you go. All right. And there's actually a space weather gal that's out there. I actually, when I was down at the EMS conference, the American Meteorological Society conference, I was talking to her, and she does space weather reports on the internet and stuff. So any questions anybody has? Yes.
What does a bird like this cost, roughly?
What does it cost?
Yeah.
I usually don't tell that because it's kind of,
I know,
it's proprietary information. So.
but it's billion plus.
The entire GOES program is at the NOAA line level, which is the spacecraft, the ground system, all the operational costs, all the scientists, is upwards of a little over $10 billion. So that gets apportioned out across everything, and that goes into the future to 2030 or 2035, right, to operate the satellite. Yes, you had a question?
So,
Oh, hang on one
you got
second.
10 years on this one, right?
Uh-huh.
So are you working on the next one?
We're building 4 of them.
Advisor.
Yeah, we're building 4 of them.
Okay.
So we've launched 2. The other 2 we have in various stages of construction in the clean room. And so the next one will launch in 2021-ish. And then the one after that, the notional launch date is around 2024. Okay?
Will they be identical?
They're all identical. And the way that I describe it is you have identical twins, and they go through life and they suffer different scrapes and scratches. And they all, you know, they're identical, but they have a few different scars here and there. That's the same way, yeah, so they're identical.
That quote in Contact where he said, I build one, and you can build 4 at 4 times the price.
Yeah, they actually are, they get much less expensive as you build a 2, 3, and 4.
The
Yeah.
quality of the camera, and as you're doing each, it's not a generation that you're building each, do you improve the camera each time?
No, it's the same thing. It's the same thing. The reason is because while we like to have improved resolution in our cameras, the scientists like data continuity, right? So it was an incredible upheaval for them to go from the previous version to this version, because all that data has to get ingested into the weather models, right? And you've now changed, if you're coming with different satellites with different resolutions and different capability, right? The weather models have to be able to handle that, right? So they did a wholesale change, right? And they'll fly it for 20 years or so. They'll do another wholesale change, right? Yes?
You were speaking of, you've answered half my question. They come out in versions, like aircraft carriers have 5 that are like, we're up to 16. how many are just like 16?
4.
Okay.
So there's 4. So there'll be 3. There's 2 on orbit. There'll be a 3rd. And then there'll be a 4th on the ground waiting to go up in case something happens to one of the 3.
And that's been common in its history, about 4 at a time?
Yeah, the last set, they built 3. The previous set, I think they built 4.
Do they have a version number at all? Or?
Yeah, so 16,
Well,
17.
that's too close to 50, but I didn't know if they had names, you know, or
No, they're called, like it'll be called Goes East. It right now goes, 16 is called Goes East. Then it will be called Goes West. And then the one that's in the middle will still retain its numerical number, which will be Goes 18. So, yeah. Yeah.
The one that's on the ground to be a backup, what happens to that if they never use it? What's done with it at that point?
A lot of times they'll launch it, and like the not only, for example, one of the older satellites, they're debating, because it was still good, right? So they moved it over the east, so over the Atlantic Ocean, so that it's not in the same orbital slot, and it's still taking data. They'll decide whether maybe the military might want it, maybe they might want to do this, that, or the other thing with it. So, yeah. So yes.
I may have missed it, but what is keeping the Go 17 from being operational right now?
They're just doing checkouts, getting it all checked out. Yeah, so they check it out. It's like on the cusp of going operational. So yes.
What did you fly for the solar panels? Is that pretty much polymorph silicon or multispectral?
They're gallium arsenide. So yes.
Any focus on the other side of the year?
Any what?
You're paying attention to North and South America. What about the rest of it?
So the Koreans just launched a satellite called GeoComSat, which has an ABI on it. The somebody else has one. Oh, the Japanese have one called Himawari. So they've got 2 Himawari satellites over there. And then the Europeans are building the EUMETSAT satellites. So they will be launching EUMETSAT in 2 or 3 years. The Japanese satellite and the Korean satellite do. The Europeans are building their own. And yeah, you can take the imagery is, we share the imagery, the weather imagery. I mean, it's one of the few things that we do really cooperate well across the world with is weather data. Okay, I mean, all of the polar orbiting satellites, everybody uses the polar orbiting satellite data. Everybody has different models, right? The Europeans have one model, we have another model, the Japanese have another model, right? And so, but we all share the same data. So we actually cooperate really well. So, yes.
So you said earlier that it goes down to Maryland. Is one site sufficient to max out the transmission bandwidth of the satellite for the amount of data that it's ingesting?
Mm-hmm.
Okay.
Yeah, and there's backups. There's a backup site in West Virginia, and so, but it all comes through. Primarily, all comes through Suitland, Maryland. There's a national satellite operations facility there. So, yes.
So what kind of capabilities are being planned for the future?
NOAA's in the process right now of looking at what their architecture is. And so there's an architecture study that they're doing to decide, do they want to disaggregate instead of putting all their instruments on one satellite? Do they want to have a bunch of little satellites? Do they want to have just a satellite over the center of the country and do some stuff on the edges? So they're trying to figure out from a cost-benefit ratio what would be the most beneficial, especially with the advent of CubeSats and smaller satellites. What's the best thing to go do? In a lot of cases, the imagery, you want imagery that's a half a kilometer on the surface of the Earth. Your aperture's got to be this big, right? That doesn't fit on a CubeSat, right? Unless you're going to do some type of synthetic aperture where you array a bunch of smaller ones, okay? The other thing too is it's not necessarily about size and about the resolution on the surface, okay? There's other kinds of measurements that you can take that when you plug them into the numerical weather models, they do better, okay, than just shrinking the pixel size. And so they're off studying all that kind of stuff to come up with what the optimal set should be for the next generation. So, you had your hand up, yes?
This is not about like satellites on Earth, but
One. That was the one that he just talked about. Nope, just one to Pluto.
Are there any really bad Ghostbusters jokes that goes around your office, being gozers?
Yeah, there's all kinds of
There's a few.
there's all kinds of stuff like that. Yeah. All right. Yes.
What finally determines the lifetime of the spacecraft? Is it propellant and things?
Yeah, I mean, we have it, we've loaded, there's, what ultimately determines it is how long the hardware lasts in the propellant, right? It's designed to last for 15 years, so it'll last longer. We've got 20 years of propellant loaded on the satellite. So it lasts for a good long time. Fuel, once it's launched, fuel is gold. So you can do all kinds of stuff that you've never imagined if you have enough fuel on board. Yes?
I was curious, as you kind of mentioned the modeling, but as you push these predictive models to try to get a longer chance for folks to see what's coming, what does that entail? Is that like an artificial intelligence kind of thing? Versus somebody looking at a computer monitor going, here comes the cloud?
I'm not the right person to answer that, but I will tell you that there's a lot of that kind of stuff going on, right? It's like, what can you do with artificial intelligence? What can you do with computing power? What can you do with different kind of data amalgamation to emphasize or, because you think about it, you've got a zillion pieces of data that come in and feed these models that they initialize them with, right? And so depending upon the weightings that they put on there, right, there's all kinds of things that they're off looking at to see what can make the predictions better. Because there's the argument that the Europeans have a better model than us, or we have a better model than them. And so everybody's constantly trying to look at it. If you go to some of the conferences, right, there are lots of papers about here's what you have to do, and here's some suggestions and things like that. So.
And that's NOAA that does that?
Yeah, NOAA. Yeah, so, NOAA, which by the way is not funded due to the shutdown right now, there's an incredible capability for the National Weather Service has not only for developing this kind of data, right, but also disseminating it out to the public. And I promise those folks that I always end by saying this, that all of this technology, all the money that we spend on developing these satellites and predicting the weather is absolutely useless if nobody pays attention to it. Okay? And so the important stuff is that, the prediction models are pretty good. And when they say that there's going to be severe weather, there's probably going to be severe weather, and you should really think about doing something about it. The National Weather Service has an effort called Weather Ready Nation that says we should be ready to heed the warnings and do something about it, because if we don't, all of this, everything we talked about, is wasted. So thank you very much. Thank you.